You never know. This one could just be hit out of the ballpark. Let's just quickly recall the Bohr model. His postulates and his model of the atom were able to explain the phenomena that Rutherford's couldn't. The spectral emissions were used for nearly 100 years before they figured out what was actually happening. Okay? Remember that your hydrogen is the simplest atom, and there's a very nice equation that gives us the energy levels. The more complicated the atom, there's no equation, and it just becomes empirical energy levels. Okay? So you would probably see this in a test or an exam. It is a very nice, reliable go-to energy level diagram. Recall the Lyman series are photons that are caused when an electron drops to the ground state. The Balmer series are photons that are emitted when electrons are dropped to N2, and then N3 is infrared. Okay? Recall, I gave you a very lovely poster on the second page of that booklet that gives you the approximate ranges of wavelengths for red, green, orange, yellow, blue, green, indigo, violet. That's not in your data sheet. Okay, so we're going to go through an example today where you might not be able to answer the question unless you were given those ranges. You're not expected to know 400 to 700. You're not expected to know 3.11 eV and 1.77 eV. But they're good to know. Okay? And then lastly, before we jump into it, be careful on the wordings. Okay? So depending on what you are asked, very different results. Okay? From N5 is literally dropping from N5, or transition from 5 to ground state, you write them all in. Okay? Now, here we get to methods of how can we excite our electrons up from lower states. Oh, what just happened? Help. 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 Okay. Could we get to here, please? There are two main methods of how we can promote our electrons up. And the simplest way to describe it is in reverse. If we said we have an electron at a higher state and it decays down to a lower state, it emits a photon of light. Now in physics, most phenomena can be played in reverse, and the physics works. So go backwards now. Let's say a photon was to come in and strike an electron in a lower state. It may promote that electron up to a higher state. But here is the problem. Only if it has the energy corresponding to an allowed transition. Okay? So it has to be exactly that energy. So that's the problem. That if let's look at a very simple diagram. I'm just going to draw two energy levels. I don't even know which one they might be. Let's just go negative 4 eV and negative 3 eV. Okay? Please put that down. Now, if we had a photon that came through with 1 eV, and if it's just in the right place at just the right time, that electron is going to basically capture that ripple of electromagnetic radiation, and it can jump up to that higher level. Because obviously it requires exactly 1 eV to be promoted to the higher level, and the photon has exactly 1 eV. If we had a 1.1 eV photon, it would not. It would just go sailing through, okay? Because providing the other transitions, there are no transitions corresponding to 1.1 eV, then that photon would not be captured. Likewise, a 0.9 eV, oh dear, I'll try that again. A 0.9 eV would as well keep going off, not captured. Okay? It has to be exactly that. As we will learn when we do the standard model, there is a fundamental link between electrons and photons. Okay? And we already figured that out. The photoelectric effect was suggesting that effect, that the photon was somehow interacting with the electron, giving it energy. Okay? So we're mediating energy. So now, I don't know if I drew anything over on this side, so let's, okay. Now we'll move on. Okay, so it has to be exactly that energy. It's all or nothing. Either it's 1 eV or nothing else. Unless it has enough energy to ionize that electron. Okay, so anything above, the electron can capture that photon and then travel off with kinetic energy. That's pretty much what the photoelectric effect was saying. So for photons, it's basically the simplest thing to remember is it's all or nothing unless ionizing. So if we had, let's just draw now negative 4 eV to 0 eV, that would be n equals infinity. Imagine we had our little electron sitting here, and along comes a 5 eV photon. Now in that case, it will get it out of the electron. Okay? It's almost the same as the energy of your photon equals your work function plus the kinetic energy. Okay? It's not really the work function, because the definition of the work function is the energy required to liberate the least bound electron in a metal. This would be sort of negative, well, it's sort of, what could we put it as? We could put it as E n minus E infinity, so negative 4 minus 0, negative En, I don't know. We'll get a little bit of maths going on here. But logically we could say, well, if a 5 eV comes in and 4 eV is required to get it to n infinity, then the remaining 1 eV is going to be traveling off with kinetic energy, 1 eV. Okay, so that can occur. So anything above 4 eV in this very simple diagram, any photons could interact with an electron. The more energetic they are, the more kinetic energy your electron would have as it flies off. Yes?
Why is there 5 eV like
Why is the 5 eV? I didn't hear.
It's like it's still got more energy than like.
Yeah, but it's above the ionizing. So if we're at negative 4, anything above 4 eV, that electron could capture and then travel off with kinetic energy. It's conservation of energy. Okay? But that's so again, remember Bohr said that an electron can't exist between those levels. So what we're saying with the 1.1, it's like saying to capture the 1.1, this electron would have to exist at negative 2.9. And the Bohr postulate said that this atom is not allowed to exist. The electrons are not allowed to exist at negative 2.9. They can only exist at finite levels. Okay? So that is why the electron will not interact. Okay, this is why, remember I said yesterday, things get weird. At this level, the rules are different. This is quantum mechanics. This is not classical mechanics. Classical mechanics says that my pen can exist anywhere between the floor and the table. Quantum mechanics says it's either floor or table, but nowhere in between. Yes?
Is there no way that only part of the photon can be observed?
Nope. No. So next, okay, there is some momentum scattering later on, but in this situation, no. The photon won't just go, here, I'll give you 2 eV, and then go and stretch out to a 3 eV. No, we don't get 5 eV to 3 eV. It's all or nothing unless ionizing. Okay? So let's just quickly look at an example. Yeah, last lesson we learnt that hydrogen, the ground state is negative 13.6. Okay, so just a very simple diagram again. Negative 13.6, 0. In comes our photon. And then obviously that residual energy is going to be as kinetic. So energy of photon equals, well, what would the equation be? E infinity minus E1. Yeah, that works. Plus EK. So that's 0 minus 13.6 is 15 plus EK. EK equals blah. I'm bad at maths. 1.4 EV. Okay. Now this could be expected. You could be expected to know this is just conservation of energy. Okay. But then the one next step is, well, why stop there? Let's find velocity. So we can rearrange EK is a half mv squared. So v is square root 2ek over m. That's year 10 stuff. The problem here is, for v, energy must be in joules. All right. So if they ever ask you to go back to this old school kinetic energy equation, remember we've got meters per second and kilograms. So we need our energy unit in kilogram meters squared per second squared. Remember that's the derived unit of the joule, meters, kilogram meters squared per second squared. We've got to convert it. If we left it in EV, then this has a Coulomb stuck in there somewhere. I don't know what the SI units for energy in EV would be. There's a Coulomb stuck there. And down here, there's no Coulomb. So just remember that we have to convert. Okay? So quickly, let's just multiply 1.4 I'll race ya. 2.24, thank you. Whoops. Mass of your electron is given in the data sheet. And if anyone wants to race me, I'm not a racist. I'll race anyone. Ha ha ha. Ha ha ha. Ha ha ha.
Right, this one is getting uploaded.
7. Delete this. 7.01 times 10 to the 5 meters per second. Okay, I have seen a variant of that joke. I'm not a racist. I love all races except marathons. F marathons. Screw marathons. No one likes marathons. Now, ha ha ha. One other thing to note. All is good here if your velocity is less than 10% the speed of light, that is less than 3 by 10 to the 7 meters per second, then we don't have to worry about nasty things like relativistic effects. Okay? So, generally at this level, we haven't done relativity yet, and if you were asked to calculate speeds of little charged particles as they whiz through or are ejected from atoms, I need to make sure that I'm not giving you anything above 3 by 10 to the 7. Okay? I did a quick little side mission at the other class, with the other class. This tube is a 4,000 volt DC tube, so the electrons as they boil off the negative terminal, they are accelerated across a 4,000 volt potential. They gain 4,000 EVs. In energy, that's 4,000 times 1.60 times 10 to the negative 19. And then if you were to do that, 2 lots of that divided by that, you end up getting a value greater than 10% the speed of light. And that is not the right answer. Once you go above 10%, we need to take relativistic effects into account. From his frame of reference, time slows down and momentum increases, and they appear to get heavier, and so they don't get that fast. We'll look at that later. But, have a think. There's no limit to what velocity can be. We can just make more and more energy. And so if this was the only equation, at some energy level, your kinetic velocity would be greater than the speed of light. And we know that that's not the case. That's the speed limit. We can't go any faster than that. There is a really cool factor called the Lorentz factor that you can throw into your equation that basically it asymptotes. It does not let you go faster than the speed of light. And that factor becomes significant above this speed. Okay? So when Mr. Murray makes his tests and his exams for like a little proton is accelerated across or determine the speed of the electron, I've got to make sure that it's below that number. Okay? So that's just a little useless story for you. Now, before we move on, I'd like you to just look at the screen here. We're just going to look at absorption because remember I said your emission spectra is one way. That's the electrons decaying to lower orbitals, spitting out discrete wavelengths of light because the energy levels are fixed. Let's play it backwards. If the photons of light came in of fixed energy levels, then those electrons would get promoted up and we would see an absorption spectrum. Okay? And obviously you might have learned in year 10 that the emission and absorption spectrum of an atom or a molecule are basically contrasts, right? They're contrast opposites. But if we were to look at this, we've got the smear of colour. We've got a continuous spectrum. So in order to make an absorption spectrum, here's what we need to do. We're going to take a hot object. Through incandescence, it produces that black body curve, right? And we know the Wien's law says the hotter the temperature, the greater the intensity, and the wavelength is shifted to the shorter end. So remember, this guy is pumping out one of these bad boys. All right, your black body curve. Now, fire that is a continuous spectrum, and if you pointed your spectroscope outside yesterday, you would have seen that smear of colour. If you pointed it at the light bulb, you would have seen that smear of colour. In that continuous spectrum is all possible wavelengths and frequencies of light. That's handy, because remember our electron or our atom is picky. It will only pick the energies that correspond to the allowed transitions, okay? So remember your incandescence, that's caused by all of the jiggling particles, and you've got so many particles and so many modes of jiggle that it's continuous, it's not discrete. So you've got this nice smooth bell curve. Now, pass that continuous light of all possible wavelengths and frequencies through our cold gas, a sample of gas. And that gas will go, oh, look, there's a 1 eV. I can take that, boop, 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 promote your electron. And another electron in another atom might go, oh, I can take that 4.3, boop, 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 take that, promote that up to a higher level. Then that continuous spectrum passes through our little diffraction grating. And so what is seen on the screen is the continuous spectrum, but the absent lines are those missing photons that the electrons captured. Does that make sense? Cool beans. At the back of the class, Mr. Angus has set up a compound that is good at stealing certain photons of light that are in the visible spectrum, which is handy because we can see the visible spectrum. So, back row. 6 of you at the back row, come up please. And we'll do this one at a time. Guys, I would like you to do 2 things. Here at look above the liquid, you will see the continuous spectrum, then drop your spectroscope down and oh my God, tell me what you see. Okay? Tell me what you see. Well, don't, but you guys will see it in a second. Okay? So, while they're doing that quietly, here's something that students often ponder. And I would like you to think. Now, those electrons grab the photons. They are excited up to higher states. But they don't stay there. All right? They will decay back down a little amount of time later, a nanosecond, a picosecond later. They would fall back down. And they would spit out a photon of the same energy. So you go, well, hang on. Why would, if I absorb, let's just say that's a 1.9 eV photon, and then it falls back down, why does that 1.9 eV photon simply fill in the gap? Does anyone think they know the answer to that? The answer is, this is absent. When the electron decays back down, it spits out that same wavelength. All right, next row, you can go and have a look. But you've got to look at the probability of which direction it's going to be ejected. It's flip a coin of what X direction it points, flip a coin of what Y direction, polar coordinates, your spherical stuff. It's a random chance. It could go, for all we know, it could go flying out that way, or that way, or that way, Very rarely would one of those re-emitted photons that's missing from our continuous spectrum actually be emitted into your spectrometer to fill in the gap. Okay? So that is why these wavelengths, these photons are re-emitted, but in a completely random direction. Okay? Which is why when you look through the potassium permanganate, you're going to see those missing bands. Those photons are now flying off into the classroom and they're not entering your spectrometer. Okay? All right, if the second row now would like to go up and have a look-see through, just quietly because we're going to keep on talking here. So, this is why you see the screen, the smear of colour with the missing bands, but I'd like you to appreciate that this is what a digital spectrometer would actually measure. You've got the intensity of your blackbody curve, and then there's missing gaps. Okay? So not only do we see that the absorption and emission spectra of hydrogen, the peaks are the same, they're also in the same proportion. What this is telling us is this is going to be an electron that's going the opposite. So instead of going from 3 down to 2, this was because of an electron went from 2 up to 3. And this one was 2 up to 4. And this one was 2 up to 5, if that makes sense. Not only that, you can see that it is more likely that an electron would exist at lower states, because there were more electrons that were at 2 that got pushed up to 3. There were less electrons at 2 that got pushed up to 4. Less electrons of 2 that were pushed up to 5. So it tells you some information about the probability of what event is going to occur. Okay? Not only that, front row, if you'd like to go and have a look at the... So again, look at the white light source. You see the continuous spectrum. Drop it down through the potassium permanganate and you'll see the bands suddenly disappear. They appear, but that's the absence of light. Yes? A drink! Has all this absorption spectra got you thirsty? Go on then. But personally, I think you're wasting your time and due to this unpreparedness, disorganisation. You're welcome. I'm having a good time here. All right. So I spoke about that absorptions. Okay. There was a lovely question a few years ago. It's getting older and older and older. Students will occasionally bring it up in preparation for this test coming in the exam. That it asks, of the 3 objects, tell me whether you would see a line or a band, an emission or absorption, discrete and continuous. Okay, so we're like, okay, energized objects emit. Cold objects absorb. So the emission absorption. Discrete and continuous. Okay, discrete is your atomic stuff with the Bohr model. Continuous is black body stuff with hot objects. But then there's a mention of band versus fine. And that comes down to molecules. So if I just, could you please... Yeah, I know. Fine. Band and fine. Let's just find a spot to write that. In fact, I think we should go back to that page 26, where, here it is. Let's just go somewhere around here. Line absorption is typically elements. Band absorption is typically, or broad band is typically molecules. Okay? So, per esempio, on this poster here, at the bottom you've got absorption. These all happen to be, well, the bottom ones are all molecules. And you can see chlorophyll has a massive band. They're very, very wide. Okay? Now, that's as far as you need to know. Elements typically are fine light absorption and emission, and molecules typically are band absorption. the easiest way to explain it is if you have a compound or a molecule, you've got your atoms, and then between we have the electrons that forms the bond, all right? It's the electrons that are bouncing backwards and forwards around the atoms. Those electrons can exist in a range of areas between the two atoms. They're zigzagging and racing backwards and forwards at very, very fast speeds. Relativistic speeds, in fact. And so, depending on where the electron is relative to the atom, it can have a range of energies. So it's not a nice energy level diagram where you have lines, 2.2 down to 1.8. It's going to be a band of energy depending on where the electron is at one time. Okay? So, if you are ever given energy level diagrams, they are going to be very simple atoms, or sometimes they're just made up. And so sometimes it says, consider the hypothetical one electron atom, and here are its energy levels. And then use the Bohr postulates to figure out what it would emit. Okay, so things do get tricky. Things get nasty. One tricky thing was brought up in the other lesson. A student said to me, Joseph Bonadeo, he didn't say that, but he goes, how come there's a big gap here? Why is there a wide band? You've just told me that that electron is only going to take a fixed value. And the answer was very quickly proposed and then confirmed with Wikipedia. Not by me, but by these nerdy students.
The probes didn't fit in, they're so close together.
No, here's the thing. Your electron in your sample, even though it's a cold gas, your atoms are still jiggling backwards and forwards. And so your electrons can be moving forwards or backwards relative to the light. And so depending on its direction, it's the relativistic velocity. And so if it's moving towards the light, that light might be blue shifted and it'll go, you know what, I'll have that, thank you very much. Or if it's traveling away, it might be red shifted slightly and it goes, you know what, you're just the right energy for me, relativistically, and it gets absorbed. But relative to us, there's going to be a slight band. So again, some really weird, interesting relativistic effects explain why that is a large band, even though it should really be a thin band. Now, cold gas. They always say cold gas. That just needs to be colder. Relative to the source. Have a think. If my incandescent globe was, say, 2000 Kelvin, and my gas was 2000 Kelvin, then obviously the electrons, what would happen is the photons might be captured by the atoms, and theoretically you would fill in, these gaps would be produced. But then if the object is at the same temperature, it's going to make its own black body curve, and it's just going to fill in those gaps by its own jiggling. Okay? So you wouldn't get the missing bands because the black body curve of the hot object would just fill those bands in. Okay? So they always say cold gas, cold sample, hot object, which is what we had at the back of the classroom. Now, there's a really fun... No, that's not what I wanted. What the... You son of a... You piece of work. Thank you. Stupid. There's a really fun image. These are known as the Fraunhofer lines. This was back in the 1800s. German physicist, don't know his first name, Wikipedia will have it. Fraunhofer took his very, very precise spectrometer. He loved it, J-Bon. It was his prized possession. He pointed it at the sun, and he got this. Now, what this is the black body curve of the sun, but lots and lots of missing objects. And there was about 590 of them, and a lot of the prominent ones he labelled and named. Since then, more precision measurements have been made. There's about 1,000 of them, but when he did it 100 years ago, about 570 or something. This was the absorption, because looky here. Here is my previously produced diagram. The sun is the hot object. The atmosphere of the sun, which extends out very, very far, that is a little bit cooler. Okay? So what was happening is the sun is pumping out its black body curve, which, surface temperature, 5,500 Kelvin. The cold atmosphere, some of the atoms were going yoink, 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 I'll take that. And so then the remaining wavelengths gets to Earth, and then the Earth also has an atmosphere. And inside the atmosphere, molecules will be saying, yep, thank you, water vapor, carbon dioxide, ozone, nitrogen, thank you, thank you, thank you. And eventually, this is what gets down to his spectroscope. All of the wavelengths that didn't get a date to the prom. Oh, they just travelled through the spectrometer. All of the other wavelengths were absorbed. This is where they went to their catalogue and went, oh, look, in the sun you've got hydrogen and beryllium and carbon and nitrogen and oxygen, and our sun pumps out about the top 12 elements. To get the heavier stuff, you've got to have larger stars dying. Ours is not big enough. But, again, there were some wide bands here. Okay? These were caused not by any molecules in the sun. Oh my God, chlorophyll. No, the Earth's atmosphere has some compounds and some molecules. Okay? So, had he been able to get into a satellite and point his spectroscope, if he could go above the atmosphere and do the same image again, you would see a certain fraction of these absorption bands disappear. And then you would just be getting the absorption spectra of the sun's atmosphere. Okay? So I thought I would just show you that. There are some major Fraunhofer lines, and some of them are the helium-Balmer series. I'll give you a moment to try and identify them. No, I'm just kidding. Oh, there they are. It's in the blood. C, F, G prime, and H. That's alpha, beta, gamma, delta lines of the Balmer series. So these were some prominent ones. Pesky oxygen. Okay. Anywho, very, very famous image. Again, helped us understand what the sun's made of and what our atmosphere is made of.
Have they done this experiment outside of the atmosphere?
Yeah. So the satellites that they launch, some of them would have pointed at the sun and gotten all of the spectral, the spectra of the sun, and then the absorption spectra that comes with it. All right, let's move on. I won't talk for too much longer, but let's get into an example. Now, in tomorrow's lesson, or when I see you next, we'll look at the other way of exciting electrons. But now let's just look. We said, all right, with photons, it's all or nothing unless ionizing. So let's just go to a question over the page where we can look at this. Oh, in fact, we could have answered this question yesterday afternoon. Oops. Oh well. Let's have a look at this one. It glows a bright yellow. Now, to remove any ambiguity, the second page of your booklet has that graph from Lucarelli, Marcelli, Marconi. Could somebody find that spectrum poster on the... And at the top, there's the Roy G. Biv, and it has the ranges of colour. Could somebody find for me the range of yellow? It was like 590...
570, 590.
Thank you very much. See, really, that's what we need to answer this question properly, because there was a bit of ambiguity. So now, determine the energy transition responsible for the intense yellow flame. So that's just your energy is N minus M equals HC on lambda. That's the Bohr postulate, that the difference in the transitions produces a photon. So, let's just do, before we jump in, let's eliminate the non-visible ones. Because you lot have your knowledge that red is as low as 1.77 and violet is as high as 3.11. So, let's do some eliminations. Which of these that I've drawn would be ultraviolet? Definitely this one. Definitely that one. Get your calculator out if you need some help, because I'm not good with numbers. 3.75. No, that's ultraviolet. What about this one? That's 1.8. That one's visible. Okay? So let me try and draw that a little bit nicer. Visible light, UV, UV, UV. All right, let's go to the next one. What about these boys? That first one is 1.64. That's infrared. The next one, visible. And then visible. Let's look at the last two. Or three. Definitely infrared, and definitely infrared. So we're down to that one, and this one. Okay? So you're going to have to do a few things for me, please, in the next 5 minutes. Figure out the energies of the transitions, and then write them down here and rearrange for the lambda. If the lambda is in that range, then it's the yellow. That's the one responsible for the yellow color. Okay? So let's do... I know this one is not responsible because it's 3 EV. It's violet. That's a violet wavelength. So automatically I'm excluding that. So we're down to... Sorry, wrong one. We're down to this one, which is 2.3, and this one, which is 2. Yeah? So they're close, 2.3 and 2. I don't know which one's green, I don't know which one's yellow, I don't know which one's orange. So, okay, could you do that, please? Split the page into 2. Find me the energy from, well, what do we got? We got N1, N2. Energy 2 to 1. And then energy 4 to 2. Okay? So get going, please. And I need to do attendance because we're missing people. Okay? So again, show all of you working out. E2 take E1 equals HC on lambda. Since we have the energy in EV, we're going to need Planck's constant in EV. This one, it's 2.3. Sean, is Campbell alright? Apparently he's sick. Haven't seen it? Okay. Oh, geography excursion, that's what it is. And Rippy is in excursion 2. Right.
What was the yellow, sir?
So the post,
580, 590. Yeah.
the poster on the inside first page says that, and that's what we're going to use. All right, let me now play catch up. Could somebody tell me what the energy was for 2 to 1?
2.11 electron volts.
So lambda equals HC over 2.11. And what do we get?
5.89.
All right, so 5.89, 10 to the negative 7, that's 589 nanometers, which I think we've just answered the question. It was this one. But let's just finish it off. Could somebody tell me the energy from 4 to 2? Thank you. I mean, that's 10% more, so I'm expecting the wavelength to be 10% less. What do we get? 554. All right. So, using the poster, this one's probably green. That one is probably yellow. Did we all get that? Now, there's no real rule for why. There could be a couple of reasons. We saw that there were 3 possible visible photons, and it might be that just as they are being sent to our eyeballs, we get an equal amount of each 3, and we just see a mixture of colours. Okay? So you could get, you've done mixtures in year 2. You throw in red with purple, you get brown, I don't know. Yeah. The other option is what we see with the diagram that I like you all to appreciate is something like that. If that's the relative intensity that reaches our eyes, we see it as red, even though there's less and less and less. There are blue and violet. We see it as red, okay? So again, it can be either a mixture of colours, or it can be that one of those transitions might be more probable than the others, okay? We'll leave it there because I'd love for you to help me out. I need to try the science quiz.